Hi, my name is Gyuwon Kim, and I'm a master's student from Pohang University of Science and Technology in South Korea. Today I'll be presenting my research titled Deep Learning Enables Accelerated Optical Coherence Tomography Angiography. This study was conducted by collaborative research teams from Pohang University of Science and Technology and Chungang University in South Korea. For the contents of today's presentation, I will first briefly introduce the basic principles of optical coherence tomography angiography, or OCTA in short, and the motivation of the current study. Next, I will explain the data acquisition process and the proposed deep learning framework in detail. Then I will discuss the experimental results and conclude the presentation with some remarks. In this section, I will briefly introduce the basic principles of optical coherence tomography angiography and the motivation of the current study. Optical coherence tomography, or OCT in short, is an essential biomedical imaging technique based on low coherence interferometry to image biological tissues. It enables non-invasive, depth-resolved imaging by demodulating backscattered light interference. The ability to resolve exile structure superiorly has led to various clinical applications such as neurology, ophthalmology, dermatology, gastroenterology, and cardiology. OCT has also been extended to functional angiography, namely Optical Coherence Tomography Angiography, or OCTA in short, to study vascular diseases. OCTA extracts the variations in OCT signals caused by the red blood cell motion to contrast blood flow within vessels against the static tissue. This functional angiography is accomplished using a sequence of repeated B scans taken from a single cross-sectional location. The agent-free OCTA modality, owing to its micro-level spatial resolution and non-invasive nature, has enabled anatomical and functional imaging in various clinical applications. However, one limitation of OCTA is acquisition speed, bound by the scanning principles employed, that is, point-by-point raster scanning and the requirement of sequential B scans. Since high-speed imaging is very desirable for functional imaging, a branch of study has emerged focusing on developing OCT systems with ultra-high imaging speed, for example, high-speed optical sources and detection devices. However, enhancing imaging speed using hardware adjustments is cost-prohibitive and may pose limitations for practical clinical system implementations. Recently, several studies have been conducted to enhance the OCTA imaging speed through advances of emerging deep learning-based methods. Such studies aim to provide software-only solutions that require no modifications to the hardware settings. One study adopted convolutional neural network architectures to accelerate the B-scan repetition procedure by reconstructing high-quality cross-sectional angiograms from a limited number of B-scans. Another study conducted pixel-wise super-resolution in the in-fast plane using deep learning to reduce the sampling density while preserving the pixel resolution. Although deep learning-based methods have demonstrated the effectiveness in accelerating the OCTA procedure, some aspects require further investigation, which has motivated the current study. First of all factors related to the imaging speed, that is, the sampling density and the B-scan repetition number, should be considered simultaneously in a single framework. The previous works addressed only one of the mentioned factors. Secondly, a deep learning framework specific to the application should be designed using state-of-the-art deep learning principles to enhance the desired performance. Previous works, while showed feasibility, mostly utilized already existing networks designed for other applications such as denoising. Therefore, elaborate image-to-image translation techniques, such as architecture and loss function design, should be considered to establish a framework suited for the current application. In this section, the OCTA dataset acquisition method is briefly described, followed by overall explanations of deep learning-based methodologies and the proposed approaches workflow. The figure illustrates a schematic of our deep learning framework for accelerated OCTA. The input to our deep learning framework consists of in-fast angiograms from 2 repeated downsampled B scans and thus are low in resolution and quality. The intermediate ground truth angiograms consist of in-fast angiograms from 2 repeated fully sampled B scans and thus are high in resolution but low in quality. The final ground truth angiograms consist of in-fast angiograms from 8 repeated fully sampled B scans and thus are high in resolution and quality. By progressively mapping to the ground truth angiograms, we conduct super resolution and quality enhancement in a single integrated framework, thus compensating for both the sampling density and the B-scan repetition process. Our dataset comprises in vivo brain microvasculature images of male mice. The samples were imaged using a custom-designed spectral domain OCT system, and system specifications are provided as follows. First, high-resolution, high-quality angiograms were obtained from 8 repeated B scans from fully sampled volumes. We chose to utilize 8 sequential B scans since it is known that the angiogram quality saturates near 8 repeated B scans. Next, we downsampled the structural volumes in the in-fast plane, and low-resolution, low-quality angiograms were obtained from 2 repeated B scans from downsampled volumes. The downsampling procedure mimics the OCTA system's raster scanning principle. For example, if the artificial scanning step size is 2 times larger than the fully sampled step size, we downsample each axis in the in-fast plane by a ratio of 2. We investigated downsampling ratios of 2, 4, and 8 in this study. In total, 29 pairs of volumetric angiograms were obtained from 11 different biosamples. We used 2,000 depth-wise sectioned in-fast angiograms from 7 volumetric volumes as our training and validation data. 200 sectioned in-fast angiograms were used from an independent volumetric pair to conduct a comparative study amongst our proposed models, and 21 maximum intensity projection, or MIP in-fast angiograms from the remaining volumetric pairs were utilized to evaluate the selected methods. We have developed an end-to-end convolutional neural network framework to reconstruct high-resolution, high-quality in-fast angiograms from their low-resolution, low-quality counterparts. As shown in the figure, our reconstruction model is structured in 2 stages and contains 2 constituent modules that operate in series. That is the super resolution module followed by the quality enhancing module. The super resolution module compensates the pixel undersampling, and the quality enhancing module compensates the B-scan repetition number. Our goal is to establish an end-to-end framework consisting of 2 submodules performing each task successively. The 2-stage design should and has in our experiments been found to demonstrate better reconstruction performance than directly mapping low-resolution, low-quality angiograms to their high-resolution, high-quality counterparts. The super resolution module first upsamples the pixel resolution of the undersampled, low-quality angiograms to their fully sampled, low-quality counterparts. Note that low-resolution, low-quality angiograms and high-resolution, low-quality angiograms are constructed from 2 repeated B scans and therefore of poor quality. Thus, the task of mapping low-resolution, low-quality angiograms to their high-resolution, low-quality counterparts is conducting pixel-wise super resolution to fill in the missing pixels from undersampling. The quality enhancing module enhances the fully sampled low-quality output from the previous module and reconstructs the fully sampled high-quality angiograms. The module specifically compensates for the B-scan repetition number and thus enhances the angiogram quality. The modules are concatenated in series to form a single reconstruction network. Throughout the network, high-level residuals are extracted using a series of repeated operations within the deep layer. We established 2 comparative network models based on the interblock connection type adopted in the deep layer: the dense connection-based models and the residual connection-based models. Several training strategies were employed to train our networks and optimize their trainable parameters. we propose a perceptually improved loss function by combining different loss terms. In addition to the primary mean absolute error loss function, we incorporate two other loss terms to aid in reconstructing the high-frequency details. The first term is the multi-scale structural similarity loss. The MS-SIM loss is advantageous because it preserves the contrast in high-frequency regions when utilized with the MAE loss. The second term is the Fourier MAE loss, which calculates the MAE from the magnitude of the angiogram's 2D Fourier transforms. We choose FMAE to provide information on the vessel orientations and perceive the downsampling remnants as frequency corruptions. The general strategy in incorporating different loss terms is that the primary loss function reconstructs the overall structure and the angiogram's low-frequency components, while the two sub-loss terms reconstruct the high-frequency details and remove the angiogram's frequency space artifacts. Our proposed loss function should and has in our experiments been found to provide improved reconstruction performance and training stability than solely using the MAE loss. Each module is sequentially trained during each iteration. The super resolution module is trained first, followed by the quality enhancing module using the previous module's output. At the end of each iteration, the two modules are concatenated as an end-to-end network and fine-tuned using a lower learning rate. After successfully establishing our DNNs, we further trained the networks using an adversarial training scheme to boost their reconstruction performance. We define a discriminator network, which we optimized in an alternating manner with our pre-trained reconstruction network. The idea is that we train our reconstruction model to fool the discriminator that distinguishes the reconstructed angiograms from their high-resolution, high-quality counterparts. The proposed training strategy allows our reconstruction model to create perceptually superior solutions residing in the manifold of the high-resolution, high-quality angiograms. The established comparative networks are denoted as ResReconstNet, DenseReconstNet, ResReconstGen, and DenseReconstGen. In this section, we present and discuss the experimental results of our octa reconstruction method. We emphasize that our task differs from image super resolution in the strict sense because our method compensates for both the pixel undersampling and the B-scan repetition number. We compare our method with existing super resolution methods, including interpolation-based image upsampling methods, and a previously reported deep learning-based super resolution network for retinal OCT angiograms called High Resolution Angiogram Reconstruction Network, or HARNET in short. We first quantitatively compare the reconstruction performance of the presented methods using the test dataset consisting of sectioned and fast angiograms. Once the methods showing the most promising results are identified, we further assess quantitative and qualitative results on the test dataset consisting of MIP and fast angiograms. To emphasize the advantage of our proposed training strategy, which is two-stage training with the perceptual loss function followed by an adversarial training, we conduct a full ablation study in addition to the comparative study with the baseline methods, and quantitative results are summarized. The models trained with our proposed training strategy outperform all baseline methods, including the interpolation-based methods and the previously reported HARNET. When solely using the MAE loss, the networks trained with the two-stage training scheme show improved performance over those trained in a single-stage manner that directly maps low-resolution, low-quality angiograms to their high-resolution, high-quality counterparts. The two-stage training strategy enhances the reconstruction performance since it provides additional intermediate supervision during training to perform super-resolution to high-resolution, low-quality angiograms. Furthermore, the table shows that training with our proposed perceptual loss function and the adversarial training scheme further boosts the reconstruction performance as the metrics improved over the two-stage networks trained solely using the MAE loss. The results follow the intuition that the sub-loss terms and the adversarial loss push the reconstructed results to the high-resolution, high-quality angiograms manifold. The dense connection-based models outperform the residual connection-based models, which is consistent with the consensus that deeper networks benefit from their ability to model mappings of higher complexity. dense recon scan consistently shows the best performance amongst all comparative methods for each of the downsampling ratios. HARNET shows the best performance amongst the baseline methods, and the bicubic interpolation method outperforms all other interpolation-based methods. Therefore, we focus our analysis on comparing the three methods for assessing the MIP test dataset, and the results are presented in the following section. We compare the performance of the dense recon scan, HARNET, and the bicubic interpolation method for the test dataset consisting of MIP and FOSS images taken from various biosamples. A bilateral filter was applied to the bicubic interpolation results to enhance the angiogram quality for fair comparisons with the deep learning-based methods. The results indicate that our dense recon scan is superior to the baseline methods in terms of the image reconstruction measures and angiogram quality measures for all downsampling ratios. We also compare the computation time and the mean frames per second rate is provided. Although our deep learning model is very deep with a high parameter dimension, it achieves a reasonably fast computation time during inference because the forward path of a trained deep learning model comprises only basic operations and nonlinear activation functions. Although the bicubic interpolation method with bilateral filtering offers the fastest computation time, it shows the worst reconstruction performance. Our dense recon scan shows the best reconstruction results while offering computation speed sufficient for real-time embedded software usage. While high-resolution, high-quality octa's mean acquisition time was 17.8 seconds, the acquisition time reduced significantly for the low-resolution, low-quality octa case. For example, doubling the scanning step size and using 2 sequential B scans would result in a 16 times faster acquisition time, which is approximately 1.1 seconds. Similarly, ratios of 4 and 8 would result in 64 times and 256 times faster acquisition time, which is 0.28 and 0.07 seconds, respectively. The figure illustrates the qualitative performance of our dense recon scan and HARNET on a low-resolution, low-quality MIP and FOSS angiogram with a downsampling ratio of 2. In the enlarged regions of interest, it can be seen that HARNET suffers from contrast loss and oversmooths the vascular details, resulting in dilated vessel structures, while dense recon scan demonstrates improved reconstruction precision with obvious advantages in recovering the high-frequency microvascular details owing to our improved training strategy. We specifically compared the reconstruction performance of very small vessels along the dashed lines within each ROI. It can be observed that the low-resolution, low-quality angiogram exhibits distorted and out-of-phase vessel profiles due to spatial aliasing. HARNET fails to distinguish vessels of small diameters and severely loses contrast. Conversely, dense recon scan reconstructs in-phase microvascular profiles with relatively small contrast loss. In addition, the vessel profiles indicate that our dense recon scan produces no false blood flow signals. We present a qualitative comparison of the two methods at higher downsampling ratios of 4 and 8. A clear distinction can be made regarding the quality of vesselness, as the difference between the two methods become more significant with sparse data. At a downsampling ratio of 4, oversmoothing and contrast loss worsens for HARNET, whereas microvascular structure and contrast are reasonably preserved for our dense recon scan. Similarly, at a downsampling ratio of 8, HARNET exhibits biologically dubious features, including jagged and disjointed vessels, while our dense recon scan reconstructs smoother and rounder vessel profiles. However, at such a high downsampling ratio, the performance of our model deteriorates severely. Since the downsampling ratio of 8 is equivalent to a scanning step size of 80 micrometers, and the scanning step size far exceeds the maximum Nyquist limit required to capture the capillary resolution, the degraded results are expected. Thus, the desired application context should always be considered when selecting the appropriate scanning step size to meet the desired performance. For example, a large scanning step size is more appropriate for clinical applications requiring fast imaging speed but tolerant to the low image quality. Now moving on to the conclusions. This study proposed a deep learning-based, software-only solution to accelerate the OCTA system's imaging speed while preserving the image quality. We tackled all existing inherent factors related to the OCTA imaging speed in a single end-to-end framework, including the sampling density and the B-scan repetition number. As a result, our approach achieved an acceleration of OCTA imaging by factors up to 16 to 256 times. Our method is advantageous since it can be directly applied to clinically available systems without increasing the system complexity. In addition, larger field of views can be captured to improve clinical observations without sacrificing the spatial resolution. We also established a novel deep learning framework by leveraging state-of-the-art deep learning principles, such as network architectures, loss functions, and training strategies, and showed that our proposed method significantly outperformed the baseline methods, including the previously reported HARNet, in both quantitative and qualitative aspects. In the future, we aim to utilize our framework for preclinical and clinical findings and applications. We also aim to extend our framework to other pathological applications such as retinal angiography or other imaging modalities such as photoacoustic imaging. By combining our established framework with transfer learning techniques, we can avoid acquiring a large amount of data that is required for retraining. We hope to utilize our integrated framework to broaden OCTA systems' clinical applicability to rapidly and accurately delineate pathological biomarkers and achieve potential near real-time functional imaging capability. Thank you for your attention. Feel free to contact my email for any questions.